Hello everyone. This is our second part of the equivalent circuit of the induction motor. Here I'm going to discuss about the remaining part of equivalent circuit of an induction motor, and after that I will also give the equivalent circuit of induction motor using IEEE a specification. What IEEE has given equivalent circuit model of an induction motor, that I will also represent it. So this in the first part, all everything has been explained, and this is part 2. Here I'm going to explain how induction motor equivalent circuit further can be simplified, and also I will explain in this model Thevenin equivalent circuit of induction motor also. So this is a shunt parameter IC, and this is I1 and I2 is the secondary or rotor current referred to the stator side. This is the rotor reactance referred to the stator side. This is rotor resistance referred to the stator side. And this is the load component or rotational component of the induction motor. So this part is shown here. So this portion is called a stator portion. This is called air gap or magnetic circuit. And this portion is called a rotor circuit. And this is our mechanical load and rotational losses. These are the various components that has already been discussed in part 1 of the induction motor equivalent circuit. Here I will also give the description box so that you can refer part 1 of the equivalent circuit also, and it is mandatory to go for the part 1 if you want to understand the concept behind it. So part 1 has to be studied first, then part 2 will be the helpful to understand the concepts. So since this is the simplified model of IEEE recommended equivalent circuit. So in IEEE recommended circuit, RC has been neglected here. Only I phi is there. Means the value of RC is small as compared to X phi, the component of the current. So that part has been removed, and this is the IEEE recommended equivalent circuit. Core loss resistance is removed, but core power loss is still considered in the calculation of the efficiency. Core loss component removed, but power calculation is present here, and if we will use it to calculate efficiency also. This so now we can see here that pi type equivalent circuit. This circuit is pi and T type equivalent circuit that will be studied in power system subject, and pi and T equivalent circuits are there. So this is a pi equivalent circuit because it looks like pi. So pi, it's look like pi means like this. So this portion and this portion, it is like a pi circuit. Everything is same here. R1 is resistance of the stator, X1 is the reactance, and this is X2 dash, and this is R2 dash, and I2 dash is the current of the rotor circuit referred to stator side, and this portion is the rotational losses or mechanical losses, and this E2 dash is the rotor voltage referred to the stator side. So now this R1 and X1, this R1 and X1 where I1 current is flowing, this portion is shifted this side. This portion is shifted this side. IC is shifted for a small value of IC. If we consider its value is small, we can shift it here, and it is shifted here. I1 has here IC value is the core loss component. I1 value will not be affected if I shift it here, because I1 is the summation of IC, and I1 is the summation of you can see here I1 is the summation of IC plus I2 dash for this circuit. Here it is again same thing. Here if I1, IC plus I2 dash. So the shifting from this place to this place does not affect much more. Now this portion R1 is here and X1 is here, X2 dash and I2 dash. The same, everything is same. Only where this portion has been shifted to left side for the calculation simplification only. So now after simplification, now this equivalent circuit, this resistance, whole resistance R1 plus X1 is called Z equivalent 1, and this is called Z equivalent 2 dash. R and X, summation of R and X is impedance here, and X is also impedance, that is slightly reduced. X equivalent and R equivalent means X1 and X2 are connected together, and that X1 and X2 is called X equivalent, and R1 plus R2 dash is called R equivalent. So these two equivalents are shown here, and this is our mechanical loss component that is now written here. So this is I2 dash. So now X equivalent plus R equivalent, and this X equivalent plus R equivalent will be Z equivalent. So now we can consider for Thevenin equivalent also. The circuit can be Thevenized like this. Here R1 is the resistance of the stator, X1 is the reactance of the stator, and using the concept of IEEE equivalent circuit, Xm is given here, and I2 dash, X2 dash, R2 dash by S. So when we Thévenize this circuit at this position, Thevenin equivalent, suppose if we want to find the Thevenin equivalent, then Thevenin equivalent means only one resistance and one reactance will be there. So we have to Thévenize this circuit, and we can find very easily the Thevenin equivalent of this circuit. For the Thevenin equivalent, what we do, we have already studied in first year. We have to short it, and we have to see from here to here Thevenin equivalent. So this portion and uh, this portion and this portion will be in parallel. These two portions will be in parallel, and parallel. If we find this parallel equivalent, so this will be in parallel. So R1 plus JX1 in parallel with JXM, and when these two are in parallel, so we will get an equivalent circuit. We will consist of RTH and plus JXTH. So just after solving, we will get two values. One real component will be there, another imaginary component will be there. That remaining real component is called RTH, and imaginary component will be called as XTH. And after this calculation, again we are connecting this our load side, that is being connected here. And after this getting this value, we will get the equivalent circuit of the Thevenin equivalent circuit. So based on this, we will be able, so we have to Thévenize this equivalent circuit, and then load side again we have to connect it, and after connection this we can find this the value of I2 dash, and this is the Thevenin voltage. So I2 dash we can find very easily. I2 dash equal to VTH, Thevenin voltage, divided by RTH plus JXTH plus X2 dash plus R2 dash by S. So this real component will be connected together, and this imaginary component will be connected together, and we will find the Thevenin load current using the Thevenin equivalent circuit. So this Thevenization gives us the simplification of the circuit. So now this Thevenized circuit is given here. So this Thevenized circuit is now we can see it very easily what Thevenin equivalent circuit is given here, Thevenin equivalent circuit. In order to simplify computation, V1, R1, X1 and Xm can be replaced by Thevenin equivalent circuit values already explained in previous slide as shown. So this come like this. This is here our air gap is there. So now VTH is V1 is here. So VTH we can also find by using the simple principle. When this load side is removed, and here our VTH side is here, we have to find VTH in the previous circuit. We have to find the here we can find very easily the Thevenin voltage here, Thevenin voltage. When we remove this side, and we have to find Thevenin voltage at this terminal, so VTH will be simply equal to this voltage V1 multiplied by JXM divided by summation of, because when this part is removed, this whole thing will be in series. So r1 plus j x1 plus xm, and x1 and xm values are known, so vth can be found, that is given in the next slide. So vth is magnitude is like this, and if r1 square is very very less than x1 plus xm whole square, as is usually the case, so this value r1 is very very small, so r1 can be ignored here, and a square root will be removed, so vth will be approximately xm divided by x1 plus xm multiplied by vm. This term is represented by kth. This is kth term is, this is kth, and now our vth is calculated. So this is our vth. This simplification has been included in this. So the first year part that you have already studied, you should remind it that how to Theveninize a circuit. The equivalent impedance, already told, the equivalent impedance zth already in this part already explained. So this and this will be in parallel, the whole thing already written, this whole thing r1 plus jx1 parallel jxm. So this parallel equivalent circuit is given here, and two branches are in parallel, so multiplying these two part and adding this, after simplification we will get its two component rth and jxth. So this again we are applying the relation r1 is square is very very less than x1 plus xm whole square, as is usually the case. So we will get, after simplification, this relation, we will get this rth equal to this much, and since x1 is very very small as compared to xm, so xth will be equal to almost equal to x1. So we got this two value, rth is this much and xth is this much. So now we have Thevenized our circuit. rth is known and xth is known, so finally we can get the value of this load, this rotor current, that is this rotor current. Finally we can get the rotor current by using the relation. That relation is rotor current I2, we can get very easily, I2 dash equal to vth divided by rth plus xth jxth plus x2 dash jx2 dash plus r2 dash by s. So by getting this value, now we will be able to find the loss in this resistance, that we will see in later part of the video, how to find the loss in this part. So loss will be in this part, I2 dash square multiplied by r2 by s. So this will we will see in the next part of the video.